Your phone charges, your GPS locks, your plant grows. Every second, quantum physics runs your life and you never notice. The weird rules that govern atoms smaller than light itself are not locked in labs. They are in your pocket, in your bloodstream. In the bird flying overhead, 7 quantum effects happening right now in objects you touch every day. Which ones control your mutations? Which ones let a robin see invisible fields? What happens when circuits the size of your hand start tunneling like single atoms? This is documented physics, measured in labs from Berkeley to Oldenburg, proven in experiments you can replicate, embedded in technologies worth $2 trillion by 2035, according to McKinsey. The quantum revolution is not coming. It arrived decades ago, and it has been hiding in plain sight. Also, comment from which city you are hearing this from. Also, this script is researched and factual using sources from Nature Physics, published in 2010, detailing quantum entanglement in photosynthetic light harvesting complexes by Saravar, Ishizaki, Fleming, and Whaley at Berkeley Lab, and from the Nobel Prize press release from October 7, 2025, recognizing John Clark, Michel Devarret, and John Martinez for macroscopic quantum tunneling discoveries. These are not popular science summaries. These are peer-reviewed findings from institutions that set the standard. Now back to the information. They cool it to near absolute zero, minus 273 degrees Celsius, a few millikelvin above the point where all motion stops. At that temperature, thermal noise dies. Quantum effects take over. The circuit contains billions of electrons, paired as Cooper pairs, moving as one quantum object. In classical physics, a particle cannot cross a barrier higher than its energy. But these billions of electrons, acting as a single wave, tunnel straight through an insulating layer called a Josephson junction. The zero voltage state traps current like a ball behind a wall. Then suddenly, voltage appears. The system escaped by tunneling, not climbing. The measurement is clean. October 7th, 2025, the Nobel Committee awards them the Physics Prize for proving macroscopic quantum tunneling exists in systems visible to the naked eye. Tunnel diodes enable high-speed switches and telecommunications at gigahertz frequencies. The effect powers magnetic resonance imaging, quantum sensors, for detecting minute magnetic and electric field changes in medical diagnosis and materials analysis. Nuclear fusion research studies proton tunneling to improve reactor designs. Without quantum tunneling, your computer would not remember anything, your phone screen would not light up, and doctors could not see inside your body without cutting you open. Not continuous, discrete. The committee notes these devices are big enough to be held in the hand, yet they behave like single quantum particles. Physicist Ephraim Steinberg at Toronto says it is some of the first evidence quantum mechanics describes not just the very small, but the mesoscopic world of billions of electrons, potentially our larger world as well. The technology that seemed impossible in the 1980s now defines the semiconductor industry. Researchers at University of Melbourne in May 2024 purified silicon chips to silicon-28 isotope concentrations, above 99.95%, removing rogue silicon-29 nuclei that disrupt quantum coherence. Single qubit coherence in silicon now holds 30 seconds. Plenty of time for error-free quantum calculations. Superconducting quantum computers from IBM, Google, and others employ these tunneling principles directly. Google's Willow quantum chip, announced December 2024, solves complex calculations in under 5 minutes that would require classical supercomputers 10 to the 25th years. That is a 1 followed by 25 zeros, longer than the age of the universe. All made possible by quantum tunneling demonstrated in those Berkeley circuits 40 years ago. A squid can measure magnetic fields billions of times weaker than Earth's field. This sensitivity comes directly from the quantum tunneling Clark studied. The device operates at liquid helium temperatures, 4 Kelvin, where superconductors conduct with zero resistance. Current flows in a loop, split between 2 Josephson junctions. The phase difference between the superconducting wave functions in the 2 paths creates interference patterns, exquisitely sensitive to magnetic flux. Hospitals use SQUIDs in magnetoencephalography, MEG, mapping brain activity with millisecond temporal resolution, and millimeter spatial resolution. No other technology comes close. Geophysicists use SQUIDs to prospect for minerals and oil by detecting tiny magnetic anomalies underground. Quantum tunneling, proven in a Berkeley lab circuit, now diagnoses epilepsy and finds natural resources. The semiconductor industry adopted tunneling deliberately once transistors shrunk past 45 nanometer nodes around 2008. Before that, tunneling was leakage, a problem to minimize. But at 22 nanometers, 14 nanometers, 10 nanometers, 7 nanometers, 5 nanometers, 3 nanometers, tunneling becomes unavoidable. Gate oxides approach atomic thickness, 5 atoms thick at 5 nanometer nodes. Electrons tunnel straight through. Engineers had 2 choices: fight tunneling with new materials like high K dielectrics, which increase effective barrier thickness, or embraced tunneling and design around it. The industry did both. High-K dielectrics, materials with high dielectric constants like hafnium oxide, replaced silicon dioxide in gates around 2007. This slowed tunneling leakage at a given thickness, but it could not stop it. So researchers developed tunnel FETs, TFETs, where tunneling is the desired mechanism. Published designs show TFETs operating at lower voltages than MOSFETs, reducing power consumption by a factor of 10 in some applications. They have not replaced MOSFETs yet. Manufacturing challenges remain. But prototypes work. The physics is sound. Within a decade, your laptop could run on transistors that tunnel as their primary mode of operation, not a side effect to manage. They study the Fenner-Matthews-Olson photosynthetic light harvesting protein complex, found in green sulfur bacteria, 7 pigment molecules, chemistry well characterized. When sunlight hits chlorophyll in plants, photons transfer energy to reaction centers with near 100% efficiency. Classical physics cannot explain it. Energy should scatter, lose coherence, degrade as it moves through the chaotic wet chemistry of a cell at 300 Kelvin. Instead, it travels almost perfectly. The team combines Fleming's light harvesting dynamics model with Whaley and Saravar's quantum information research. They find numerical evidence for quantum entanglement in the FMO complex persisting over picosecond timescales, essentially until excitation energy gets trapped by the reaction center, picoseconds, trillionths of a second. But at biological temperatures in a noisy, disordered system, this is remarkable. Multi-particle entanglement exists long enough to route energy through the most efficient pathway, testing multiple routes simultaneously, collapsing to the best one. While there have been prior investigations of entanglement in toy systems motivated by biology, this is the first instance in which entanglement has been examined and quantified in a real biological system. Entanglement is the quantum interconnection of two or more objects separated in physical space. Measure one, you instantly know the state of the other, regardless of distance. Einstein called it spooky action at a distance. But in photosynthesis, it is not spooky. It is functional. Pigment molecules in the light harvesting antenna become entangled. Energy explores all possible pathways at once in superposition. When the system collapses to the pathway with least resistance, energy arrives at the reaction center with minimal loss. Efficiency hits 95% or more. Published simulations in the Journal of Chemical Physics confirm the mechanism. Computer models show chromophores, the pigment molecules, maintain quantum coherence long enough to guide energy transfer. Gregory Scholes at University of Toronto shows marine algae use a similar trick. The quantum states in these systems are relatively long-lived even at room temperature in complicated biological environments. In quantum lab experiments, the slightest intrusion destroys superposition. But plants evolve to protect coherence. Protein scaffolds shield the quantum process from environmental noise. Evolution spent 3 billion years perfecting this. The paper was published in May 2010 and remains the standard reference. The implications extend beyond plants. Artificial photosynthesis researchers aim to replicate these quantum processes for solar energy. If we build solar cells that mimic leaf quantum coherence, efficiency jumps. A study in Science Advances used two-dimensional electronic spectroscopy to observe energy transfer in light harvesting complexes, revealing quantum coherence. Optimizes the process. This could revolutionize renewable energy. Instead of 15 to 20% efficiency in current panels, we approach biological levels, over 90%. The quantum advantage is real, measurable, and already running in every plant cell right now. In photosynthetic proteins, at room temperature and water, coherence lasts long enough to complete energy transfer. How? The protein structure creates an environment that actually enhances quantum effects rather than destroying them. Researchers studying this phenomenon found that noise in biological systems, instead of being purely destructive, can be dynamically optimized. Specific vibrational modes in the protein scaffold couple to the electronic transitions in chromophores, guiding energy transfer. This is environment-assisted quantum transport. The environment, normally the enemy of quantum coherence, becomes an ally. Evolution tuned the protein structure over billions of years to create this condition. Studies using femtosecond laser spectroscopy capture snapshots of the process. Pump probe experiments show quantum beating patterns, oscillations, in the signal that reveal coherent superposition of multiple pathways. These experiments do not happen in theory. They happen in real protein samples at 300 Kelvin. The data is unambiguous. The vibration-assisted tunneling hypothesis suggests that odorant molecules cause electron tunneling in olfactory receptors based on molecular vibrational frequencies. Smell something, an electron tunnels. Different molecules have different vibrational signatures, different tunneling rates, different smells. This remains more controversial than photosynthesis entanglement. Evidence is mixed. Some experiments support it, others do not. But the fact that it is even plausible shows how far quantum biology has come. 20 years ago, suggesting quantum effects in warm, wet biology got you laughed out of conferences. Now it is mainstream enough that researchers design experiments to test it. Turin's group published work suggesting deuterated odorants, where hydrogen is replaced with deuterium. Smell different because deuterium changes vibrational frequencies, altering tunneling rates. Critics argue the effect is small or non-existent. The debate continues, but photosynthesis entanglement is settled science. Published, replicated, accepted. Now back to the quantum facts. Exactly 9,192,631,770 cycles per second for cesium. 1 second is defined by that count. Atomic clocks lose 1 second every billion years. GPS works because satellites broadcast timestamps. Your phone receives signals from multiple satellites, each with exact time data. Triangulation determines position. Even a tiny error, say 1 microsecond, translates to 300 meters of position error. Quantum mechanics makes the precision possible. Without quantized atomic energy levels, the clocks drift. Without relativistic corrections accounting for time dilation, GPS fails within minutes. Satellites experience weaker gravity than ground level, so their clocks gain about 45 microseconds per day compared to ground-based clocks. General relativity. Adjust for it, or your map app sends you into a lake. This improves precision. Researchers now create entangled atomic clocks. Link multiple atoms via entanglement, and when you measure one, you effectively measure all. This reduces quantum noise. Several groups have surpassed the standard quantum limit using entangled atoms. Quantum 2.0 technologies use both superposition and entanglement as resources. NIST is developing quantum networks that distribute entanglement via optical fibers across metropolitan areas or between continents using satellites. The Washington, D.C. Area Quantum Network, DCQNet, includes NIST, NASA, and defense labs. Scientists use atomic clocks to reduce noise effects in optical fibers and ensure photons arrive at destinations at the right time. Jonyet Jaila envisions a global network of entangled space clocks, providing a time standard far more accurate than GPS and enabling geodesy and underground sensing with unrivaled accuracy. Lasers split each atom into a superposition state, simultaneously traveling 2 paths, then recombined. Since the atom behaves as a wave, these paths interfere, creating a pattern encoding detailed information about motion, rotation, and acceleration. Classical inertial navigation drifts over time. Quantum sensors offer orders of magnitude greater sensitivity. This quantum inertial navigation does not rely on satellite signals. It cannot be jammed, spoofed, or disabled. Underwater, where GPS signals do not penetrate, submarines could navigate with quantum precision. The atomic clock inside the quantum sensor maintains coherence for timescales needed to complete the navigation. This is quantum superposition put to work in defense, aviation, and eventually consumer devices. MESA. Quantum raised $3.7 million in seed funding in September 2024 to miniaturized chip-scale atomic clocks to fit inside smartphones. Currently, golf ball sized. Goal is phone sized within this decade. Once that happens, your phone no longer depends on satellite signals. Quantum timing becomes personal. A single Apple A17 Pro chip packs 19 billion transistors in a silicon area smaller than a fingernail. Each transistor is a tiny switch controlling electrical current. Electrons flow or do not flow depending on voltage applied to a gate. Moore's law, observed since 1965, states transistor count doubles every 2 years. Not a law of physics, an observed trend. But it is slowing. Transistors shrink toward atomic scales. At 3 nanometer nodes, the gate is a few dozen atoms thick. Quantum effects that were once ignorable become dominant. Specifically, quantum tunneling. Electrons tunnel through barriers they should not cross. In old large transistors, this was rare. In modern sub-5 nanometer transistors, tunneling causes leakage current. Current flows even when the transistor should be off. This wastes power, generates heat, limits performance. But tunneling is not only a problem, engineers exploit it. Tunnel field effect transistors, TFETs, use tunneling as the core mechanism. Traditional MOSFETs, metal oxide, semiconductor field effect transistors, move electrons over an energy barrier. TFETs let electrons tunnel through a barrier. This allows lower voltage operation and less power consumption. Introduced conceptually by Leo Isaki in 1957, who won a Nobel for tunnel diode research. Flash memory, the storage in your USB stick and phone, uses tunneling to inject electrons across oxide barriers into charge trapping regions. No tunneling, no non-volatile memory. Every file saved, every photo stored relies on controlled quantum tunneling. IEEE Spectrum notes that tunneling governs how current flows across metal semiconductor contacts, essential to every semiconductor device. Alan Seabaugh at Notre Dame says the aim was to leapfrog Moore's law, but silicon technology kept advancing. Today, the rules are changing. Physical limits force innovation. Chip makers explore quantum effects deliberately, not accidentally. Intel, IBM, Samsung push TFETs and other quantum-based transistor designs. The tunneling transistor could extend Moore's law or replace it entirely. Superconducting qubits need millikelvin temperatures. Control circuitry runs at slightly higher temps but still far below room temperature. Cryo-CMOS technology merges classical and quantum. Semiconductor manufacturing adapts. Extreme ultraviolet lithography, EUV, prints features smaller than 7 nanometers. Quantum chip companies like Google, IBM, Rigetti, IonQ use semiconductor foundries to fabricate qubit arrays. The same tunneling physics that powers your laptop enables the next generation of computing. Google announced quantum supremacy in 2019 using 53 superconducting qubits. Willow chip in December 2024 reached error rates low enough for practical fault-tolerant computation. All leveraging macroscopic quantum tunneling first demonstrated in Berkeley 40 years ago. The semiconductor industry consumes over 20% of global electricity for fabrication. Transistors built on quantum tunneling reduce power consumption, but scaling to billions of devices per chip requires managing quantum noise, leakage, and coherence. The future of computing is quantum, whether we use qubits or squeeze more life from classical silicon by embracing tunneling deliberately. Quantum all the way down? Specifically, a protein called cryptochrome 4, CRY4, in the bird's retina. When blue light hits CRY4, it triggers a series of reactions, shuttling an electron around. 2 unpaired electrons form in different parts of the protein. These are called a radical pair. Each electron has a spin, up or down. The pair exists in a quantum superposition of singlet and triplet states. Singlet means spins are opposite. Triplet means spins are aligned. The radical pair oscillates between these states in what researchers call the singlet-triplet waltz. The oscillation frequency is influenced by external magnetic fields. Earth's magnetic field, though weak, is enough to alter the rate of interconversion between singlet and triplet. The bird's retina detects this change, translating magnetic field direction into a neural signal. This is the radical pair mechanism. Proposed theoretically decades ago, proven experimentally in 2021. Cry4 from non-migratory chickens and pigeons showed little magnetic response. Cry4 from migratory robins showed high sensitivity. Evolution may have optimized robin Cry4 for navigation. This is the first paper that actually shows bird cryptochrome. 4 is magnetically sensitive, says Rachel Muheim at Lund University. The quantum coherence in these radical pairs lasts over 100 microseconds. That is 1/10,000th of a second, long enough for the bird to sense the field before decoherence destroys the quantum state. Simon Benjamin in Singapore notes that coherent quantum states decay rapidly, so the challenge is holding them as long as possible. Molecular structures in the bird's compass keep states alive for at least 100 microseconds, probably much longer. The best comparable artificial molecules manage 80 microseconds at room temperature in ideal lab conditions. Evolution outperforms human engineering. Electromagnetic noise at frequencies matching the singlet-triplet oscillation scrambles the radical pair mechanism. Magnetite-based sensing, an alternative hypothesis, would not be disrupted by radio frequencies. Entanglement also makes a brief appearance in the system. The 2 electrons in the radical pair are entangled. Measure one spin, you know the other. Eric Gauger, who worked on this, says about 5 years ago they predicted spins should preserve quantum coherence on the order of 100 microseconds to be consistent with the extreme noise sensitivity of the compass. This timescale seemed very surprising. Now experiments confirm it. The Avian magnetic compass operates in cluster N, a brain region processing visual information. Disable cluster N, the robin can still use sun and star compasses, but cannot orient using the magnetic field. Magnetoreception requires vision. The protein is absent in parrots, hummingbirds, and Tyranni sabacines. Some Tyranni are long-distance migrants flying day and night like robins, but they lack Cry4. This provides a natural control group. If those birds navigate without Cry4, the hypothesis faces problems. If they have a different magnetic sense or lack one entirely, it supports the quantum mechanism in robins. Researchers now investigate magnetic orientation in Tyranni. Langebrake says they are a natural tool for understanding CRY4 function and the importance of magnetoreception in migratory birds. Quantum entanglement, superposition, radical pairs, all working inside a living eye at body temperature in the chaotic environment of a flying bird. Not a lab, not cryogenic, just biology using quantum mechanics to see invisible fields, optimized by evolution. Normally, a proton sits on one side of the bond, stabilizing the base pair. But in quantum mechanics, the proton has a non-zero probability of tunneling through the energy barrier to the other side. This creates a tautomer, a rare form of the base with altered bonding. If a tautomer persists when DNA unzips for replication, the polymerase enzyme misreads the base. It inserts the wrong complementary base on the new strand. Adenine that should pair with thymine pairs with cytosine instead. Guanine 8 pairs with thymine, point mutations, single letter errors in the genetic code. Watson and Crick suggested in 1953 that spontaneous mutation may be due to a base occasionally occurring in one of its less likely tautomeric forms. This idea circulated for decades without proof. In 2021, Louis Slocum at University of Surrey published in Physical Chemistry, Chemical Physics. The team used high-level quantum chemistry calculations to model proton transfer in DNA base pairs. They incorporated the quantum effects, allowing a proton bound to cytosine on one strand to spontaneously tunnel and hook up to guanine on the other. The calculations show quantum tunneling contributes far more to proton transfer rates than classical over-the-barrier hopping, several orders of magnitude larger. For guanine-cytosine pairs, the reverse barrier is large enough that once a proton tunnels, the tautomer stays stable for a significant portion of time, long enough to survive until DNA unzips. Adenine-thymine pairs have a small reverse barrier, so tautomers collapse immediately. But guanine-cytosine tautomers persist. If replication starts while a tautomer exists, polymerase misreads it. GC becomes G star C, star denoting tautomer. Then, during replication, G star pairs with T instead of C, mutation locked in. The model predicts hundreds of thousands of tautomers present in a cell's genome at any given time. Even though each tautomer is fleeting, so many form so frequently they become a rich source of mutations. In March 2021, an analysis in communications physics by Slocum and team at Surrey found that thermal equilibrium between canonical and tautomeric forms is reached over timescales far shorter than biological processes. Quantum tunneling dominates, not classical thermodynamics. Sam Hay at University of Manchester notes the paper uses quite high-level calculations to re-examine the phenomenon. The model does not include the full DNA double helix, just single base pairs. Nearby structures may have a significant effect, but modeling the entire strand requires enormous computational power. The work is the first to rigorously quantify quantum tunneling contribution to DNA stability. Gizem Salevi-Torabfam at Sabancı University says this could pave the way for investigating various quantum tunneling processes in DNA and cell membranes that may have fundamental importance in molecular biology. Extending the model, a study in the Journal of Physical Chemistry Letters by researchers using quantum mechanics/molecular mechanics found that in the DNA polymerase active site, a short-lived tunneling-ready configuration appears along the wobble reaction pathway. This configuration dramatically increases proton transfer rate by 100-fold. Quantum tunneling plays a critical role in determining transcription error frequency. Without tunneling, spontaneous mutation rates would be far lower. Evolution itself, driven by mutations, owes part of its mechanism to quantum effects. Experiments at University of Surrey are testing whether cells grown in deuterated water, D2O, show altered mutation rates. If quantum tunneling is involved, mutation rates should decrease when heavier isotopes are used. This is testable. Jim Al-Khalili and colleagues are running experiments now. If confirmed, it proves quantum mechanics is not just present in DNA, but actively shapes genetic stability and mutation. Every cancer, every evolutionary adaptation, every genetic disease potentially traces back to quantum tunneling events in the hydrogen bonds of DNA. About 10,000 times smaller than the diameter of a human hair. At that scale, electrons are confined to a tiny space. Quantum confinement effect kicks in. The dot's size determines its energy levels. Energy levels determine the color of light emitted. Make a cadmium selenide quantum dot 5 nanometers in diameter, it emits red light. Make it 2 nanometers, it emits blue. Same material, different size, different color. Tune emission across the entire visible spectrum just by controlling growth time during fabrication. Unlike phosphors, which are material specific and inflexible, quantum dots offer spectral tunability with one material system. Narrow emission spectrum, high color purity, nearly 100% of Reckon 2020 color gamut. Traditional phosphor-based white LED backlights emit broad spectra, wasting energy in infrared. Quantum dots cut sharp at the red edge, improving efficiency. Electroluminescent quantum dot LEDs, QD LEDs, where dots emit light directly from applied voltage, exist in labs but face longevity issues. Nanosys expects their QD electroluminescent technology available for production by 2026. Sharp NEC demonstrated 12-inch and 30-inch prototype QD LED panels at CES 2024. Performance depends on quantum dot size and composition. Indium phosphide, InP, quantum dots replace toxic cadmium-based materials. Research at Seoul National University, Fraunhofer IAP, Merck, and Osram targets InP solutions for commercial displays. Active matrix QD LED displays using inkjet printing were expected by 2020 to 2021. But as of 2024, prototypes remain in development. Mass production is close. Higher efficiency, less heat, Displays using quantum dots achieve color rendering index, CRI, near 100, matching daylight. Sungmin Jung at Cambridge developed QD LED white lighting systems with 92% CRI and color temperature range from 1612 Kelvin to 8903 Kelvin using just 4 pixelated quantum dot colors: red, green, cyan, blue. Theoretical maximum CRI of 97%. By varying quantum dot size, emission tunes from ultraviolet to infrared. 1 semiconductor material. Complete spectrum. Juanita Curtin, researcher at AMS Osram, notes, quantum dots are particles we can tune. By changing form, we influence behavior. Quantum dots are deployed in displays, fluorescent materials, security features on banknotes, and now general lighting. Currently, narrow red emitters for lighting see the most use, but applications expand. Quantum dots enable micro LEDs, microscopically small LEDs for ultra high resolution displays. Traditional phosphors cannot coat such small areas effectively. Quantum dots, being nanoscale, fit perfectly. This makes displays with pixel densities exceeding current smartphone screens possible. The quantum confinement effect is a direct consequence of quantum mechanics. Bandgap energy, the gap between valence and conduction bands in a semiconductor, is inversely proportional to the square of quantum dot in size. Larger dots have more closely spaced energy levels, emitting lower energy photons, redder color. Smaller dots have wider spacing, emitting higher energy photons, bluer color. Electrons and holes, the charge carriers in semiconductors, are confined to the dot volume. Their wave functions, quantum mechanical descriptions of particle behavior, are squeezed. This raises their energy, photon emitted. When electron and hole recombine has energy equal to the band gap. Control dot size, control band gap, control color. Precision down to atomic layers. Add or remove a single monolayer of atoms. Color shifts noticeably. Quantum dots exhibit properties of artificial atoms. Discrete energy levels, superposition states, useful in quantum computing as qubits. Quantum dot qubits use electron spin or charge state as the quantum bit. Semiconductor fabrication techniques produce quantum dots with high qubit densities. Intel, IBM, Google leverage this. Combining quantum processors with classical semiconductor control circuitry creates hybrid architectures. Classical systems handle error correction, system control, traditional calculations. Quantum processors tackle problems that exploit superposition and entanglement. Scalability is critical. Quantum dots provide a path using established semiconductor manufacturing. All happening now. Quantum tunneling lets electrons pass through barriers in your USB drive, your transistors, your DNA. Macroscopic tunneling, demonstrated at Berkeley in 1985, now powers the 2025 Nobel Prize in every solid-state drive on Earth. Quantum entanglement routes energy through plant cells with near-perfect efficiency, discovered at Berkeley in 2010, quantified in Nature Physics, replicated in marine, algae, green sulfur bacteria, every leaf on the planet. Quantum superposition in atomic clocks defines the second, times GPS satellites to nanosecond precision, tested on the X-37B in August 2025, and will replace GPS entirely within the decade. Quantum tunneling in transistors enables Moore's law at 3 nanometer nodes, with billions of switches per chip, each relying on electrons slipping through barriers they should not cross. Quantum compass in Robin Eyes uses radical pairs and entanglement to detect Earth's magnetic field, proven by Xu and Hoare in 2021, optimized by evolution over millions of years. Quantum tunneling in DNA hydrogen bonds drives spontaneous mutations, calculated by Slocum in 2021, tested in polymerase active sites, responsible for genetic variation and evolution itself. Quantum dots in displays tune color by size, deployed commercially in Samsung QLEDs, heading to mass production as electroluminescent QD-LEDs by 2026. Everyone backed by peer-reviewed research, replicated in multiple labs, published in Nature, Science, Physical Review Letters, awarded Nobel Prizes. The quantum revolution happened while we were not looking. It is not hiding anymore. Every object you touch, every device you own, every cell in your body uses quantum effects to function. The line between the quantum world and the classical world does not exist. Never did. We built that line in our minds because quantum mechanics is hard to visualize. But the math is clear. The experiments are reproducible. The technology is deployed at scale. 50 years of quantum computing research finally overcomes the error problem. Calculations that take classical supercomputers 10 septillion years, 10 to the 25th, finish in 5 minutes. That number is not exaggeration. That is published performance. Willow uses superconducting transmon qubits. Descendants of the Josephson junctions, Clark, Devoret, and Martinis, demonstrated in 1984. Same physics, scaled up. Error corrected. Commercialized. John Martinis, one of the 2025 Nobel laureates, led Google's quantum computing development and demonstrated quantum supremacy in 2019. The quantum effects discovered in Berkeley labs 40 years ago are now inside chips solving problems classical computers cannot touch. Researchers at University of Rochester use superconducting circuits with qubits, quantum units existing in multiple states at once, building on the same tunneling physics recognized by the Nobel. NIST develops quantum communication networks distributing entanglement across cities. Atomic clocks reach precision where relativistic effects at the scale of a centimeter become measurable. Jun Yi envisions quantum clock networks in space, measuring gravitational field variations, so precisely they reveal underground caves, predict volcanic eruptions, map Earth's interior without drilling. Every quantum sensor, every quantum computer, every quantum communication link traces lineage to experiments, proving quantum mechanics works in macroscopic systems. The story you were told is that quantum mechanics is weird, abstract, relevant only to physicists in labs. The real story is quantum mechanics is the operating system of reality. Transistors tunnel, atoms entangle. Proteins sense magnetic fields via quantum coherence. DNA mutates via proton tunneling. Displays emit light from quantum-confined nanocrystals. Clocks measure time using quantized atomic transitions. None of this is metaphor. None is approximation. These are the mechanisms, documented, measured, engineered, sold in stores. The quantum world is not separate from our world. It is our world. The photons hitting your retina right now are quantum. The electrons flowing through your neurons are quantum. The chemical bonds holding your DNA together are quantum. Every breath, every heartbeat, every thought runs on principles that seem impossible until you look close enough. Then you realize they are not impossible. They are inevitable. The universe does not care if quantum mechanics makes sense to you. It works anyway. The next time you look at a screen, remember, quantum dots are emitting precise colors tuned by nanometer scale confinement. The next time your DNA replicates, remember, protons are tunneling through hydrogen bonds, occasionally causing mutations that drive evolution. The next time a leaf captures sunlight, remember entangled pigment molecules are routing energy with near-perfect efficiency. It is a theory about everything, from electrons to circuits you hold in your hand to the birds flying overhead to the plants growing in your yard. The scale does not matter. The principles hold. And those principles, once considered too strange to be useful, now define the technologies worth trillions of dollars, the biological processes sustaining all life, the fundamental operations of matter and energy. You live in a quantum universe. You always have. Now you know which parts you can see.